going to look at next is transient flow, and this is the only case where we look at unsteady state first law conditions. And what I have here, and you may have experienced, is an air cleaner that you'd use on a keyboard. And if you squeeze it, the can gets cold. Now, why is that? And we're about to find out. So if I look at the first law, which is really from chapter 3, equation 352, we have that the change of the energy of the control volume, so the change of the energy of the control volume, and in this case, the control volume would be the can, and stuff would be squirting out of it, is equal to del Q minus W, del W, plus E in dm in minus E out dm out. And so what we're going to do is simplify this, and this energy of the control volume will replace as the change of the internal energy of the control volume. So we're using the familiar terminology that we've used. And first, let's discharge the tank. So if I'm going to discharge the tank, I'm going to have stuff leave it, and I'm going to simplify it by this equation. Nothing's going in, there's no work done, and so this equation, change of the energy of the control volume is equal to del Q plus HDM out. And now what we do is we typically have this be adiabatic. To find del Q, we can't find it from first law considerations. I need additional information. So typically we say that it's adiabatic. And I get rid of that. And I have that the change of the internal energy of the control volume, which is the change of the mass times the specific internal energy. So this term is this, is equal to this discharge where H is the enthalpy term. We've neglected the kinetic and potential energy. So E is equal to H plus KE plus PE. These terms go away, and we're just left with H. And this is the mass leaving, so that's the mass leaving. So then if I play around with these equations, this leads to du plus pdv is equal to 0. du plus pdv is equal to 0. This is the reversible adiabatic. So this term, this designates reversible adiabatic. So for our purposes, if we have it be an ideal gas, I have it be an ideal gas. This is true in general. Now we're going to do for an ideal gas, this is PV to the K is equal to a constant. So I can apply the ideal gas laws that we had before. So T2 is equal to T1. T2 over T1 is P2 over P1 to the K minus 1 over K. So in our case, as I discharge the can, P2 was going down, so T2 is going down. This becomes a fraction times T1, so this temperature goes down. And we have other relationships related to the mass, etc., that's in the tank. So I have T2 over T1 is equal to V1 over V2 to the K minus 1 is equal to M2 over M1 to the K minus 1. And notice that V is equal to the mass times specific volume, and that's what we have here. The mass times specific volume is equal to a constant. So the mass times its specific volume, the volume of the tank, the volume of this container does not change. The mass and the specific volume within it change. And we have the equation as well with mass and pressure and specific volume. Okay. And notice that these cross multiply and give us this term. Now if we can discharge a tank, obviously we can charge a tank. So the opposite case is where we're going to charge a tank. Charging a tank. So if I'm going to charge a tank, we're going to have a tank. We'll consider it's adiabatic. We're going to have to do that. For the same reasons that I did with discharging a tank, we need to have other means to evaluate Q than the first law. We're going to assume that the inlet enthalpy is constant. So what we're doing is the enthalpy of the fluid coming in, here's the tank, stuff's going in. We want to find the condition that's in the tank and what it is. And in the text, we called HN equal to HL. L was for line. I wish I never did it, but I did it, and so I'm stuck with it in the book. So anyway, that's where that came from. I think using HN makes more sense. If I look at the first law equation, equation 352, and I now simplify it, we have the integral of HDM in is equal to the change of the internal energy of the control volume. Better U. The change of the internal energy of the control volume. So if I do this, I know that delta U of the control volume is equal to M2U2 minus M1U1. So this is the difference in the control volume is that what the mass final times its internal energy minus the mass initial times its internal energy, the difference between them is a change of the control volume. Now we're going to evaluate this term as well. So when I look at this term, the enthalpy stays constant, and what I'm looking at here is that this term becomes H times Mn, and Mn is equal to M2 minus M1. Right? The mass final minus the mass initial is that. So we end up with our equation. So Mn times Hn is equal to M2U2 minus M1U1. We have that. If M1 equals 0, if it's empty initially, then I'll have M1, M2, Hn is equal to M2, U2. The M2's cancel, and so I have that U2 is equal to Hn. And this assumes that P2 is equal to Pn. So we're assuming that the final pressure in the tank is equal to the pressure that's coming in here. So obviously, for something to flow in, it needs an inlet pressure, which again is held constant. For an ideal gas, we have C sub B T2 is equal to C sub B Tn, where that T2 is equal to C sub P over C sub B Tn, which is equal to K times T in. So in this case, again, adiabatic, when I charge it, so I'm charging it, the tank goes in, I'm charging it, and the temperature finally in the tank is higher than the inlet temperature. This is T2. So T2 is higher, and what's happening is that the flow energy, the enthalpy term, H is equal to U plus PD, this flow work term that we talked about in chapter 3, this flow work term has to stop, and it causes the temperature to rise as all the energy associated with this term goes into the final internal energy. So we're going to charge the tank. We'll let the tank be 2 cubic meters, 100 kPa, 300 K. So this is like a tank at room temperature conditions. We're going to have a valve. We're going to be charging it with air. Again, this is all air. We're going to charge it with air at 300 K and 900 kPa. So we're interested, and I want to find out what the final temperature is. What is T2? So I'm curious as to what that final temperature is. But isn't it interesting that I have 300 K air coming in, the tank is initially at 300 K, but the final temperature will be hotter at a higher temperature than this. So let's see what's going on. So now we have to find the initial mass. We'll apply the equation. So M1 is equal to the mass in the tank. So it's P1 V1 over RT1, 100 times 2 divided by 0.287 times 300. So the mass in the tank is 2.323 kilograms. So I know that's the mass in the tank. I can apply the first law equation that we have. So I have M2 minus M1, the mass in times H in is M2 U2 minus M1 U1. So if I substitute in what I know so far, I have M2 minus 2.323 times C sub P 1.0047 times Tn 300, so this was C sub P, is equal to M2 C sub B T2 minus M2, I want to put in the number for C sub B, 0.7176 times T2 minus M1, 2.323 times C sub B, 0.7176 times 300. So I have this whole equation here that I wrote out, and when I look at this, I look and I see that I have two unknowns. I have an unknown of M2, and I have an unknown of T2. So with that, let me simplify so we can get all these numbers squished together. And I have 301.4 M2 minus 200.1 is equal to, oh, I jumped a step, minus 700.18 is equal to 0.7176 times M2 T2 minus 500.1. And now I'm going to bring this over, and we'll see what the equation looks like in a more cleaned up form. So what what I want to do is I multiplied this out, I got these terms, I can bring the 500 over, subtract it there, and then let's see what the equation looks like. 301.4 M2 minus 200.1 is equal to 0.7176 M2 T2. So now I have a question. How do I do this? Remember, this is an ideal gas, so I can always use PV equals mRT. So the reason we write this down, PV equals mRT. Oh, P2V2 would be equal to M2RT2. So now let's look at that. So we have the P2V2 is equal to M2RT2. Well, I know P2 and V2 and R, so I don't need to know this explicitly. So M2T2 is equal to P2V2 over R is equal to 900 times 2 divided by 0.287. So I have M2T2 is equal to 6,271.8. And now I could go back in and substitute in this equation for M2T2 and solve for M2. So we're going to solve. So I'm going to take this term, I'm going to stick it right back there. And so then when I do that, it enables me to solve for M2. And if I do such a thing, we have 301.4 times M2 minus 200.1 is equal to 4,500.6, or I solve for M2 and I get M2 is going to be equal to 15.6 kilograms, and T2 is equal to 402 degrees K. And basically I just I take this and I substitute back here and I get T2. So we have T2. Now, let's see what it would be, how much mass would be in the tank if the tank were empty. So we did the hard problem first. So I did the hard problem first. Now let's do the easy problem. Tank empty. So M1 equals 0. And in that case, T2 is equal to K times Tn. So it's 1.4 times 300, or T2 would be equal to 420 degrees K. So the temperature would be higher if the initial tank were empty and I charged it. So that's what we have. I wonder what the mass would be, if we'd have more mass or less mass. So let's apply the ideal gas law. M is equal to PV over RT. So M is equal to the pressure, 900, volume is 2, R is 0.287, and T2 is 420. And so the final mass is 14.9 kilograms. I'll be darned. The final mass is less than the mass in, than the final mass here. And that's because the final mass in this, so this is like, what? The tank was empty? And now there's less mass in it than if I had the tank full, but there was mass initially in the tank. So M2 reflects the fact there was mass initial, And it reflects the fact that this was at a lower temperature, and hence when I look at the ideal gas law, if T is less, M is greater. So we had two effects going on. So it's counterintuitive. So for homework, to give you something to practice in terms of counterintuitive tank charging and discharging. So for homework, 645, 647, 653, 661. So if you look at these, and this ends chapter 6.